Hey everybody, welcome back. Thanks for watching. We're going to do some linear algebra extension problems. So I want to start with the following theorem. It says, let A be an m by n matrix, then the following statements are equivalent. And I want to mention something. So in math, whenever you see the following statements are equivalent, it means this. As soon as one of these is true, the other are true as well. They follow as a result. Okay, first, so for every vector b in Rm, the equation ax equals b has a solution. So if this is true, then the other three follow. So as a result, too, every vector b in Rm is a linear combination of the columns of A. So, again, to interpret that, if this is true, then this follows as a result. So 3, the columns of A span Rm. What does that mean? The columns of A span Rm? It means if I consider all linear combinations of the columns of A, that will generate the space Rm. And then lastly, A has a pivot position in every, that should say, row. In every row. But realize if you have a statement like this where it says the following are equivalent, it also means this. If 4 is true, then the other 3 are true. So yeah, as soon as one of these is true, the other 3 follow as a result. So if 2 is true, then 1, 3, and 4 follow, etc. So yeah, as soon as I know that any of these is true, that means I get the other 3 as a result for free. So with that said, let's take a look at an example. So here we want to know how many rows of the matrix A contain a pivot position, and as a follow-up question, does the equation ax equals b have a solution for each b in R4? Okay, so let's investigate. So I'm just going to label the columns of A as column vectors. So since v1, v2, v3, and v4 are 4 vectors comprising the columns of A, then the span of the 4 equals R4 if and only if A has a pivot position in all 4 rows. So what's our method for determining this? We want to row reduce A and see if we get a pivot position in each row. If we do get a pivot position in each row, that means that the span of the columns will give me all of R4. This. Okay, so this happens when this happens. Okay, so here we go. We're going to take the matrix A and then row reduce. Now, of course, I know I keep mentioning this, but to save time, I often go from here to here, but on any test, etc., you've got to show all the steps. Show the row reduction like we did in the first week. Okay, so notice we row reduce, we get a pivot here, here, and here. Those correspond to pivot positions here, here, and here. But I don't have a pivot position in each row. Since I do not have a pivot position in each row, it means that the columns of A do not span R4. And so what does that mean if the columns do not span R4? Well, it means there's going to be vectors that are in R4 which can't be expressed as a linear combo of the columns. So it's like vectors are left out of the party. Okay, so let's do another question. So another question revolving span. Okay, so here I've got 3 column vectors from R3, and the question is, does this set span R3? What does that mean if a set spans R3? It means, is it the case that when I compute the span, the set of all linear combos of these vectors, is it the case that I generate R3? And that's the big question. Okay, so what's our method for determining this? we're going to put this into a matrix, and then we're going to row reduce, and we're going to look and see if the rows have a pivot position for each row. Okay, so we investigate exactly this matrix A. Okay, so here we go. So there, we put the columns here, right here, and then we row reduce, of course, show this on any test. We land here. So this is almost completely reduced. This is not quite in reduced row echelon form, but it is in row echelon form. But more importantly, I can see the pivot positions. So I've got a pivot position here, here, and here, and that corresponds to, on my matrix, here, here, and here. But notice, since every row has a pivot position, that means that this set spans R3 or generates R3. So what does that mean if the span of this equals R3? It means any vector in R3 that I choose, I can express that as a linear combo of these three. So that's what it means for a set to span. Okay, so any vector in R3 I choose. So for example, if I choose the vector 1, 2, 3, because this spans R3, that vector 1, 2, 3 can be expressed as a linear combination of these. In fact, again, the fact that there's a pivot in every row tells me that any vector that I choose in R3 can be expressed as a combination of these. Okay. Okay, so let's now do a problem involving the null space. So here we want to describe all the solutions of AX equals 0 in parametric form. Then we want to give the null space of A. So we've got quite a large matrix for A. And so how do we first solve AX equals 0? Well, to solve AX equals 0, we want to set up this matrix, and then we want to row reduce. Once this is in reduced echelon form, we're going to give the solutions in parametric form. And once we have the solutions in parametric form, it's going to be pretty easy to give the null space. Okay, so 1, 2, 3. Okay, so here we go. So we want to take our matrix A, and we're going to start to row reduce this. So I think we're actually going to show this. So we'll do this one in full. Again, for a test, anytime you have to row reduce, just as a reminder, you've got to show that. Even if in the notes it says it gives the final form, you've got to show all the steps in between. Okay, so I'm just rewriting the matrix A, and I want to remember that I need a bar and a final column of zeros because I'm solving AX equals 0. Okay, that doesn't seem so bad. It seems like it's almost in reduced row echelon form. So if I want to complete out the reduced row echelon form, let's go ahead and multiply row 3 by 8 and add it here to row 2. That's going to give me a 0 above this pivot. Okay, so this sum will replace R2. Okay, so row 1 is the same. That seems good. And then row 2, I've got, looks like 0, 0, 1, minus 7, 4, 0. And then row 3 stays the same. So that's 0, 0, 0, 0, 0, 1. And then row 4 is all zeros. Okay, so that seems pretty good. I'm noticing 3 pivot positions. So above this leading 1, I want a 0. So let's just take row 2, let's multiply it by minus 2, plus row 1, and this sum will replace row 1. Okay, so that'll be 0 plus 1, 0 plus 5, minus 2 plus 2. This is going to be, it looks like 14 minus 6. This is going to be negative 8 plus 9. This is going to be 0 plus 0. So that seems pretty good. So we'll just write out the rest of our matrix. And I believe we'll now be in reduced row echelon form. Okay, so that seems good. So based on the leading ones in each row, so it looks like this is a pivot column. So this must be free. So column 2 corresponds to a free variable. This is a pivot column because that's a leading one for that row. So pivot column. This must be free. This must be free. And then this is a leading one for that row, so that's a pivot column. Okay, so it looks like I have 3 free variables. And just so I don't lose track, let's go ahead and label this x1, x2, x3, x4, x5, and x6. Okay, so now we want to write out the solutions, then give a vector, and then break it up into parametric vector form. Okay, so let's talk solutions. So x6 is, let's see here. So that's a pivot, it's not free. So just read this. It says that x6 is 0. Okay, so x5 is free. So x5 equals x5. x4 is a free variable. So x4 is equal to x4. And then we want to read this. So think about what this says. This says x3 minus 7x4 plus 4x5 equals 0. So think about solving that. Write it out if you need to. This says that x3 is equal to 7x4, because I'm adding it over to the other side. So 7x4 minus 4x5. Okay, we said that x2 is free. And then x1, to get x1, we think about this row. And so think about what this says. This says x1 plus 5x2 plus 8x4 plus x5 is equal to 0. So imagine solving that algebraically for x1. So x1, I'm going to give myself a little room here. So this must be minus 5x2 minus, looks like 8x4 minus x5. Okay, so there's my solutions, but again, I want to write this as a vector. So that's like part 1 of the solution. Okay, maybe I'll leave that for a moment. As always, pause if you need to, rewind, etc. Watch as many times as you need. Okay, so let's write this as a vector and then decompose it. The decomposition will be important not just for getting parametric vector form, but we use that decomposition to find an expression for the null space. Okay, so my vector. So all I'm doing is putting x1 in the first component, x2 in the second, etc. Okay, so x2 is free. x3 is 7x4 minus 4x5. x4 is free. x5 is free, and x6 is 0. I need to write that 0 there. So please don't think because that's 0 you don't have to write anything there. There is a 0 in that component. Okay, so we're going to break this apart. So how are we going to break this apart? We're just going to need a vector for, so I don't have any standalone constants. I don't have anything like 10, 10 minus this, or 3 plus this, or 1 plus this. So there's no standalone constants. So I'm just going to break this up into one vector per variable. I'm going to have an x2 vector, an x4 vector, and an x5 vector. Okay, so all of my x2 stuff, so that's going to be minus 5x2, 1x2, 0x2, 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 0, coefficient of x2. So you can see if you were to distribute back, you would be talking about all of the x2 stuff. Now the x4 stuff. Okay, so there's minus 8. There's 0 x4s here. There's 7 x4s here. There's 1 x4 there, 0 x4s, and 0. Okay, so that vector corresponds to the x4 stuff. And then finally, the x5 stuff. So I've got minus 1 x5, 0 x5, minus 4 x5, 0 x5s, 1 x5, 0. This is exactly parametric form or parametric vector form where the parameters are x2, x4, and x5. So remember what this represents. So before we write out the null space, remember what this represents. This represents all of the vectors that the matrix would send to 0, right? So that's exactly what this is. Okay. So yeah, so this is the collection of all vectors x that the matrix, when I multiply, will send to the 0 vector. And this is very checkable. You can pick any x2, x4, and x5, so maybe you choose 1, 2, 3. Combine this into a single vector, and then multiply a times that vector x carefully, and you should end up with the 0 vector. And specifically, you should get the 0 vector that's in R4. Okay, so now let's give the null space. Remember, the null space is the collection of all vectors that get sent to 0 by the matrix. So the null space, I can think about this in a couple ways. I can think about it as the span of these individual column vectors. So without the parameters, right, because that's included in the span. Because the span of a set is the set of all linear combinations of those vectors. Okay, so all separated here. So yeah, if I take the span of these three vectors, that's the null space, or the collection of all vectors that the matrix will send to 0 vector. And another way to write this, so instead of writing the word span, you can just remember what span means. What this actually means by definition is it's the set of all linear combinations of those three vectors. So you might be saying, how is that different than this? This is just an expression for the solution. This is the object that collects all of those. So you have to be very, very careful with your notation. Precision matters. So I can either write the span of the set, or I can actually write out the set of all linear combinations, which is actually just the definition of the span. But I have to mention these are real parameters. So x2, x4, and x5 are real parameters. And there's your null space, collection of all vectors that get sent to the 0 vector by the matrix A.